Welcome to the deep dive. If you or, your organization relies on really cutting-edge materials, could be for batteries, semiconductors, high-performance clothing, whatever, R&D can be just brutal.
Oh, absolutely. It's incredibly expensive. It takes forever. And honestly, the success rate can be shockingly low sometimes.
Right. We're talking about finding that one critical needle in
Oh,
this,
yeah.
vast, costly, experimental haystack.
And the cost of failure in material science, it's just immense. Not just the money, but the wasted time. Years sometimes.
Yeah. And the struggle today, it seems, isn't just making something, say, lighter or stronger. It's hitting all these conflicting goals at the same time.
Exactly. Like you need a fabric that repels water like crazy, lasts forever, and is totally free of those nasty PFAS
Buck River
chemicals.
chemicals.
And that traditional cycle, waiting, what, 12, 18 months for lab results? That's just a guaranteed way to fall behind your competitors.
Okay, so our mission today is to really dig into the AI revolution that's tackling this crisis head on. We're looking at what our sources call the Microsoft stack.
Three tools working together: Discovery, MatterGen, and MatterSim.
Right, Discovery, MatterGen, MatterSim. The idea is they work together to basically squash that development time from years down to months.
And crucially, they don't just speed things up. They help invent, simulate, and then decide on brand new materials,
Right.
all before you even make a physical sample.
Which is a huge shift.
It really is. It's moving away from just trial and error towards something more like agentic generative invention. Whole new strategy.
Okay, let's unpack that. Starting with the brains of the operation, you could say, Discovery.
Right.
My first thought was, okay, this just makes the usual computer chemistry stuff faster, but you're saying it's more like an enterprise platform managing the whole R&D process.
That's the core difference.
Yeah. Mm-hmm.
Scientific R&D is messy, really messy.
How so?
Well, the knowledge base is enormous. It's often contradictory. Things are really nuanced. Your standard company database just struggles with that. It treats facts like, separate little bricks. Discovery, though, it's built on this powerful graph-based knowledge engine.
A graph engine. Why is that specific architecture so important for science?
Because it reasons. It doesn't just store data. It maps out the complex, subtle relationships between data points.
Ah, I see.
It understands the results of old experiments, sure, but also the assumptions behind them, the conflicting theories maybe in scientific papers, even the structure of your own company's private research.
So it connects the dots.
Exactly. So when a researcher says, finding something with X property and Y cost, Discovery uses that whole graph to explain why it suggests a certain path. It shows its work, basically. Transparent reasoning, source tracking. It's genuinely collaborating.
And this collaboration, it happens through specialized AI agents, is that right?
Precisely. Discovery is the orchestrator, the conductor. You've got Copilot acting as the main scientific AI assistant.
Okay.
And it directs these specialist agents. Maybe one agent is a molecular properties simulation specialist, another is a sourcing feasibility agent. They do the heavy lifting.
And Discovery connects these AI agents to the big supercomputers, the HPC simulations.
Yeah, that's the other crucial piece. It links the AI insights with the massive high-performance computing needed for those really complex physics calculations.
That sounds incredibly powerful as a concept, but, does it actually work? Is there a solid proof of concept, something that tackled a really tough, maybe compliance-driven problem?
There is, actually, and it's a big one right now. Finding non-PFAS immersion coolants for data centers.
Oh, wow, yeah. With the global push to ban PFAS, that's critical.
Hugely critical. So Microsoft researchers used Discovery, and it computationally found a novel non-PFAS coolant prototype in about 200 hours.
200 hours, that's what, less than 9 days for something that usually takes months, maybe a year of lab work just to find candidates?
Exactly, just to narrow things down, yeah. And then the physical validation followed pretty quickly, too.
How quickly?
They synthesized that digital blueprint into an actual physical prototype in under 4 months. So it really validates that strategic shift. When AI kind of understands the rules of the road, the constraints, the theories, the potential dead ends, it can just explore new possibilities way, way faster than humans alone.
At that speed is just, astonishing. But Discovery, the brain, it needed something new for that coolant, right? It didn't just find an existing chemical.
Correct. It defined the criteria, but then it needed something to actually build that new molecule, digitally speaking.
And that's where MatterGen comes in. This isn't just faster screening. You called it generative invention, pure invention.
That's right. MatterGen, which was published in Nature, by the way, it moves beyond just sifting through millions of known chemicals. It's limited.
Limited to what we already know exists.
Exactly. MatterGen actually generates proposals for totally novel materials, new polymer blends, maybe coatings, composites, things that might have never existed before, all based on the specific prompts from discovery. Performance, cost, sustainability.
So, okay, you could theoretically tell MatterGen, I need a solid-state electrolyte for a new battery, high temp, and it just draws up a new molecular blueprint, one that meets those specs.
That's precisely the goal, yes.
Yeah.
It generates structures that are conditioned on the properties you want: a chemical, mechanical, electronic, whatever,
Yeah.
but also sticking to the non-negotiables, like sustainability targets or cost limits.
It still sounds a bit like science fiction. How does it actually do that? We hear diffusion model with AI image generation all the time. How does that apply to atoms?
Well, the concept is similar,
Hmm.
but yeah, applied to 3D atomic structures. An image model starts with noise, refines pixels. MatterGen starts with a sort of random atomic structure
Okay.
and uses a diffusion process to adjust the positions of atoms, the types of elements, the crystal lattice arrangement, iteratively tweaking the geometry until the predicted properties match the prompt.
And it learned how to do this from.
It was trained on structural data from about 608,000 known stable materials, so as a foundation in real chemistry.
That training data is key. But still, if it invents a structure on the computer, how do you know it's even remotely possible to make? Or stable?
Right, the validation question. That initial training set helps provide the sort of chemical common sense.
Yeah.
But the sources give a really key validation example.
Okay.
MatterGen was asked to generate a structure for a totally new material, TAC-206.
TACR206.
Okay. And it was conditioned on having a target bulk modulus of 200 gigapascals, GPa.
Right. GPA measures stiffness, basically, resistance to being squished. Crucial for durability, high pressure stuff.
Exactly. So the target was 200 GPa. When
Yeah.
collaborators actually went into the lab and made this new material,
Yeah.
the experimental measurement came back at a 169 GPa.
169 compared to a target of 200, that's pretty close.
For complex materials prediction, an error under 20% is exceptionally close, experimentally speaking. It really shows the digital invention lines up strongly with physical reality.
Okay, so that handles the invention part. Discovery, the brain, tells MatterGen, the inventor, make me stuff like this. MatterGen spits out, say, 500 potential candidates.
Yep.
But like we said at the start, testing 500 candidates physically, that kills the whole speed and cost advantage.
That's the bottleneck, absolutely. And that's why the third piece, MatterSim, is so essential.
The virtual simulation lab.
Exactly. MatterSim provides that vetting step, but in silico in the computer. It predicts how those 500 candidates from MatterGen will actually behave under real-world conditions.
And when you say real-world conditions, what kind of range are we talking about? Just like room temperature tests?
Oh, the scope is pretty staggering, actually. MatterSim uses deep learning, and it can handle simulations for metals, oxides, sulfides, even liquids across a huge range.
How huge?
Temperatures from basically absolute zero up to 5,000 Kelvin. Pressures from standard atmosphere way up to 10 million atmospheres.
10 million atmospheres. Wow. Okay, so that covers things like fusion energy research or maybe high-pressure manufacturing for semiconductors.
Definitely. Those kinds of extreme environments.
And the sources mentioned MatterSim isn't just broader in scope, it's also better, more accurate simulations.
It is. They report a tenfold increase in accuracy for predicting properties at those finite temperatures and pressures compared to older models, which is impressive on its own.
10 times more accurate.
But maybe the even bigger deal is its data efficiency.
Wait, hang on. 10 times more accurate and more data efficient. Usually you need more data for better accuracy, don't you? How does that work?
It really speaks to how well the underlying model architecture is optimized, I think. It's tuned specifically for materials physics.
Okay.
The sources give an example with simulating water, which is surprisingly complex.
Mm-hmm.
MatterSim apparently needed only 3% of the data compared to traditional methods to get the same accuracy as experiments.
Only 3% of the data. That's huge. That means simulations run much faster, cheaper.
Exactly, which feeds back into the speed of the whole system.
So you've got this loop. MatterGen explores new possibilities faster, MatterSim validates them faster. It's like a continuous flywheel accelerating itself.
That's a great way to put it, a flywheel.
Oh.
And every simulation, success or failure, feeds intelligence back into Discovery's knowledge graph.
So the whole system learns.
Constantly learns, yeah,
Yeah.
which becomes a real competitive advantage over time.
Okay, let's make this concrete for everyone listening. Let's use that end-to-end example from the sources, the R&D team at Nimbus Outdoor Apparel. Fictional company, but a realistic
A
problem.
very realistic problem.
Yeah.
They need a new water-repellent membrane for their gear.
And not just any membrane, the requirements are really tough.
Brutal, yeah. First, completely PFAS-free, non-negotiable.
Right. Then it has to survive 50 laundering cycles, 50 washes, and still work.
Plus, meet high durability targets Martindale abrasion tests, for rubbing against rocks or pack straps.
And one more, it needs at least 25% recycled or bio-derived content.
Good luck hitting all four of those with traditional R&D. That's the kind of project that usually ends in delays and frustration.
Okay, so how does the Nimbus team use this AI stack? Step one.
Step one, they upload everything into Discovery, the whole brief, the performance targets, cost limits, but also maybe historical test data, notes on what didn't work before those lessons learned.
So Discovery, the brain, digests all that and translates it into machine-readable goals.
Exactly. Step two, Discovery tells MatterGen, the inventor, generate 500 candidate coding or fabric systems that meet these goals.
And crucially, MatterGen creates them already aiming for PFAS-free and the recycled content target.
Right. Sustainability is baked in from the start, not bolted on later.
Okay, 500 candidates generated. Step three, the virtual lab.
Step three, virtual vetting. Instead of making 500 samples, Discovery sends all 500 digital candidates to MatterSim.
And MatterSim just runs them through the ringer virtually.
Yep. Virtual durability tests, flexibility at freezing temps like -10 Celsius, predicting wash durability, checking delamination risk. The works. It quickly filters those 500 down to maybe, say, 10 or 20 really promising ones.
Filters out 95% or more, just like that. Okay, step four.
Step four is the critical decision point. Discovery takes those 10-20 survivors, analyzes the simulation data, uses its knowledge graph, and surfaces the top, maybe 3 to 5 finalists.
And it explains why they're the finalists.
Yes, with detailed rationales, performance predictions, estimated costs, even checks on sourcing feasibility, like can we actually get the raw materials needed for this formula affordably?
And then comes the physical lab.
Only then. Only those top 3 to 5 really high-promise candidates go for actual physical sampling and testing.
So you skip potentially 12, 18 months of lab work on dead ends.
Precisely. All those frustrating failures are avoided.
The business impact seems obvious then. Faster innovation.
Hugely faster, compressing maybe a year and a half into a few quarters.
Massive cost savings on materials and lab time.
Huge capital efficiency, yeah.
Yeah.
Less waste.
And risk mitigation too, right?
Right.
Catching potential failures like the membrane peeling off before you make it.
Exactly. Detecting failure modes in silico. And ensuring compliance, like the PFAS-free rule, is handled proactively, not as a panicked reaction later.
And this Nimbus example, it's a peril, but the idea applies much more broadly. This is a strategic shift for any industry needing advanced materials.
Oh, absolutely. The sources make that clear. The range of applications already happening is enormous.
Like what?
Well, critical stuff. National security, energy. The Department of Energy's Pacific Northwest National Lab, PNNL, is using this platform for complex chemical separations. That's vital for nuclear science, waste management.
Okay, serious applications. What about manufacturing?
High-tech manufacturing, too. There are partnerships mentioned, like with Synopsys, aiming to speed up semiconductor design.
Makes sense. And beyond physical materials.
Well, adjacent fields, pharma, for example.
Yeah.
GSK is apparently looking at these kinds of generative platforms to accelerate finding new medicines. Even cosmetics. The Estee Lauder companies are using it to analyze their own proprietary R&D data, looking for breakthroughs in product formulation, stability, performance.
It really changes the whole dynamic, doesn't it? Instead of just picking from what suppliers offer,
Yeah, instead of being passive.
companies can actively invent and simulate exactly what they need, then figure out how to scale it.
Exactly. They design the ideal solution first. The ability to model materials under just crazy conditions, extreme heat, pressure, and then use that data to generate totally new options. It's revolutionary. It creates this self-improving engine for discovery.
It really does make you stop and think. I mean, this system sped up finding a non-PFAS coolant, helped validate a battery material. If AI can custom design new materials to hit specific environmental and performance targets before you even put on a lab coat, what's next? What's the next material that really needs replacing urgently in our supply chains? Maybe it's concrete, maybe certain plastics. And how fast could this Discovery MatterSim system actually deliver that replacement? It makes you wonder. If you had access, what would you prompt MatterGen to invent?